So you have seen all the elements at the system level. Now I'm just going to focus on the details of this wideband PAM. So this is the only wideband phase array antenna module in the market. It was intended designed to operate from 24 to 30 gigahertz with 8 by 8, 64 elements with dual polarizations. Um, so total of 128 elements in this phase array. It covers from minus 45 to plus 45 degrees in azimuth scan angle, with plus and minus 15 degrees in the elevation. The total EIRP for this PAM is 47 dBm, but that's based on the nominal bias setting. We also have the low power mode that is giving you the plus 40 dBm of the EIRP. It uses 16 volts as the DC input voltage with a very simple USB digital interface. As you can see, the picture on the left is our wideband PAM that with the cover on and the radome in front of all the antenna elements. The heatsink in the back is connected to the 8 heat pipes in the picture on the right you see here. Between each of the heat pipes, we have the antenna A module card. And all of these 8 cards are combined into the combiner card in the back. We also have a digital control board, pickle zap on the back side of this combiner card. Let's look at this plot diagram that shows the configuration of our subarrays. So starting from the right, we have a total of 8 AIM cards. Each of the AIM card consists of 8 vertical and 8 horizontal polarization elements from the top to the bottom, alternating with each other. Then this AIM card also combines and split into one receive channel and one transmit channel that are connected to the combiner card in the back. With this configuration, it results with 2 subarrays and ends up with 2 transmit channel and 2 receive channel that are complement to our DTRX2 transceiver board. This design is very flexible, as in customer wanted to have more EIRP. You can actually add more of the AIM card to boost up your output power. You can also modify the combiner or the splitter on the combiner card to modify it to your needs of the number of beans you want. So you've seen that there are a total of 8 AIM cards in this phase array. So each of the AIM card consists of the 16 antenna elements, 8 vertical and 8 horizontal elements, and followed by 16 of Otava's single pool double through switches. After that, the heart of this AIM card has 2 Otava's beamformer IC on it. And then it gets combined or split down to a single receive output channel and a single transmit input channel. We also provide the digital control through the header pin to the pickle zap board on the back side of the combiner. It also provides the DC power for the entire AIM card. This is just the block diagram of the AIM card, just to reiterate that it has vertical and horizontal elements, and then it combines down to 1 transmit and 1 receive channel. Here we are showing the details of our wideband beamformer chip. It was designed to operate 24 to 40 gigahertz cover 4 of the 5G NR2, FR2 bands, as well as LEO satellite and some of the defense applications. It provides 8 receive inputs to 1 receive output and 8 transmit outputs from 1 transmit input. It also has an independent VGA control with 20 dB of range with in a half a dB step. Also, we also built in the independent phase control to cover 360 degrees with 5.5 degree step. For this chip, we also built in the external TR switch driver to provide plus and minus 3 volts output to drive the external switch. For customer who wanted to add external 3-5 devices, such as the 3-5 PA, we also have a built-in external gate driver that operates from minus 4.3 volts to 0.3 volts. Besides all the above-mentioned functionality, we also have some analog circuit, such as the temperature sensor, RMS power detector, that will help us to monitor the chip temperature, as well as to provide some A to D, potential A to D protections. The 4-wire digital SPI design has both LVDS and CMOS control options. This interface can go up to the LVDS option can go up to 350 megahertz for fast on-the-fly switching for all the parameters. We also have a memory that can store up to 64 states for the fast beam switching. So when we design all these AIM cards and also the beamformer IC, we basically built in a lot of flexibilities for different platform for customer needs. The first option is if customer wanted to have a more total EIRP for the system, we can insert the 3-5 device, the PA and the LNA, integrated with Otava's switch OTSW100 or 101 to create this front-end modules, and it can be inserted between the antenna and our beamformer chip. In this way, you can boost the output power in the transmit channel and reduces the noise figure in the receive channel. For some system that only has receive or transmit, we can simply just remove the TR switch from the front-end module. The second option is you can increase or reduce the number of beams by modifying the combiner card, the combiner splitter on the board. In addition to all those, you can also modify the number of beamformer chip in each of the AIM card to modify the number of beams that your system needs. So thermal is a very challenging issue in any system that we have to face. So from the beginning, our team started thinking about the thermal solutions. After a few options and tweaking on the designs, we finalized on this fully passive cooling solutions. So it uses all the heat pipes over the beamformer chip and bringing the heat out through the heat pipe and then continue with the heat sink in the back. With this method, we were able to reduce the array temperature from 125 C to 75 C degrees effectively. So the last piece of this wideband PAM is the combiner card. It was designed with to complement the number of elements in this array, as well as the number of channels in our DTRX2 channels. So this combiner card takes 4 of our AIM cards and form a single subarray. That results into 2 subarrays with 2 transmit channels and 2 receive channels. The front of this combiner card connects to all 8 of the AIM cards through this blind mate SMPM connectors with the header pin that provides the DC powers and digital controls. The back of this combiner card acts as the backplane of this whole PAAM. It also provides the housing for the DC components and the digital control board PicoZ for the whole array control. So combining this PAAM with the array software GUI developed by Avnet, we can provide, this ease of use, out of the box, ready to use solution for our customers. Now you have seen all the hardware pieces. We'll show some measured data. So the data that I'm showing here were all taken in the lab setting in a controlled chamber. What I'm showing today is only going to focus on the 28 gigahertz operational frequency. So this slide shows the transmit antenna scan patterns only in the H polarization fashion. So when we are measuring the H polarization, we turn off all the vertical elements as well as the receive channel. So this side-by-side plot shows the azimuth scan from plus to minus 45 degrees on the left, and the right side shows the elevation scan from plus to 15 degrees. And they're all in the 15-degree step size. This is very similar to the H polarization, but just showing the vertical polarization scan patterns. The transmit EIRP for both polarizations is very consistent throughout this wideband from 24 to 30 gigahertz. Now showing the receive antenna scan patterns. What you see here on the left side is the H polarization, and then the right side is the vertical polarization. And they're both showing the azimuth scan from minus 45 to plus 45 degrees. And then all these data are showing a very, very good scan angle performance. Now, circling back to this top level chart, I wanted to recap all the critical components in this whole chain. So on the right, we have the wideband PAAM that covers from the antenna to analog beamforming portion of the chain. It can be connected directly to the DTRX2 on the left side, lower left side of the picture. Then the DTRX2 that does the frequency conversion can be plugged in directly with AMD's RFSoC Gen 3 development board done by Avnet. We have the other option is to insert the Otava's tunable filter in between the PAAM and the DTRX2 for band select options. We do have a separate software GUI for each of these reference kits separately. But with Avnet's existing RFSoC Explorer software platform, we can combine and modify this to include the beamforming algorithms, the wake functions, band selection for the whole array control. Thank you. I'll pass to my colleague Georgia for the MathWorks.